Let's look at a basic example of re-expressing data in order to try and do a linear fit. Let's look at this data set, and I got the scatter plot here. The question is, does it look like a linear fit? Y hat is b0 plus b1x will work well. Well, hopefully that doesn't look much like a straight line to you. Maybe it would be one straight line and another straight line, but it'd be really nice if maybe there's some re-expression of the data y that would actually make that better. Okay, so when the data is it's curving upward like this, then as the book points out, you want to start going down in the ladder of powers to try to do a re-expression. So what we could do is and this I'm going to use Fathom's ability to do this right here. Oops. I'm going to put in a formula. So on the calculator it's going to be a little different, but you can just put in like L3, and in the space for L3 at the top of the stat edit, you can put in a formula based on L2 if that's your y values. So I'm just going to put in, well, let's try y to the minus 1, or 1 over y. Okay, and now instead of graphing the y here, I'm going to go ahead and put the z in. Okay, well that seems a bit better, but now it's curving upward. Now when it's curving upward, that's often a sign that we've gone too far down in the ladder of powers. Well, we've gone to y to the minus 1 power. That was the formula for z here. That's another name for 1 over y. Well, we could back up to y to the minus 1/2 power. Now that's a weird thing to say, but it's really, there's another way to say that, and that's the square root of y, or 1 over the square root of y. Okay, and they say this is maybe one of your rarer re-expressions, but I wanted to focus on it just because I don't want to leave it out. I don't want to make it feel lonely. So let's redo the formula for z. Okay, so this is where you'd put in maybe an L4 or redo your formula in L3 based on L2. Hey, look at that. Let's see, I'm actually going to rescale the axes. That looks much, much better. Okay, so how do we use that? Well, let's see. What we've got now is our guess is that in fact 1 over the square root of y hat there we are. That is something that we're hoping to do a regression for. Okay, so that's cool. So let's go ahead and do that regression. I'm going to do that here. Least squares line does that for me. Okay, and so the z, of course, here was, I'll put a hat on it because it's just a predicted version of z. Okay, that's equal to, looks like they usually do it in a different order, but I always like to do it in the book's order. 0.0044 plus 0.323x. Awesome. Okay, so how do we use that? What the heck? What does this cryptic formula mean? Okay, well, so here's an explicit question. When x is, let's say, 4.5, I'm going to put this in the middle of the data set to avoid trying to extrapolate, although you could maybe try to extrapolate a little bit. Okay, what is our prediction for y? After all, it's y that we really care about. That's the real data. We're going to work it through z, as we'll see in a minute, but it's really our prediction for y that we want. Okay, a couple ways to do it. One is we could first predict z and then look at this relationship between the two. Or we could go all the way to y. So let me just do it two ways real quick. Okay, so our z hat is going to be, we're just going to plug in times 4.5. Okay, let's evaluate that. Okay, so that's minus, or that's now plus rather. And I wish it would put it here automatically, but it doesn't. Okay, 1.4491. Now that's not the quantity we actually wanted, but it has a simple relationship, a precise known relationship between that and the y hat. Okay, and so y hat, well, this is saying that 1 over the square root of y hat is 1.4491, and then I just have to solve. Okay, so I'm going to need to take 1 over both sides. That's one way to do it. I just take the reciprocal of this, that pops it up into the top, the numerator position, and I'm going to take the reciprocal of the other side. Whoops. Okay, and now I'm going to square both sides. So y hat is 1 over 1.4491, all squared. and that is about a half, 0.476. Okay, so let's go back to the original graph with y here. If x is 4.5, I'm predicting about a half for the y value. Okay, that's pretty good. Okay, it's definitely plausible. It's right in the right zone. Okay, but certainly looking at the z graph allows us to be more precise. Our z was 1.45 when x is 4.5. Yeah, that seems just about right. Okay. The other way to do it is just once and for all solve this for y hat. It's a little bit maybe more sophisticated. Let's just do the same thing we did on the algebra at this level. Okay. So we're going to take this and we're going to take the reciprocal of both sides. So root of y hat, just copy that in, is the reciprocal here of all this stuff. And then so y hat itself, oh, I don't want the whole thing. Oh, well, let me just delete the square root. Okay. Is all that stuff squared? So it's a more complicated formula, but it's something that fits the data pretty well. Looks like it's 1 over some linear function of x, all squared. Still something we can plug in x to our heart's content and get predictions for y without a problem. Now, when we start doing the more precise analysis of like residuals and R and meaning and stuff like that, we would sort of go back to the z level and say, okay, I'd like to really think about z, which is this new quantity, 1 over the square root of y. Because you can't necessarily say things like residuals and stuff like that for y directly. But if you just want to predict, this is our prediction of how you get an approximate predicted y value out of the x. Okay.